My name's Evan. I work at SchedgeMe, where I write Haskell and JavaScript. And before I worked at SchedgeMe, I wrote a lot of JavaScript. And if you have any doubts about that claim, you can look for my name in this series of books. And if you're looking to learn more about some of the kind of inner workings of JavaScript, this guy actually does a great job, so I would check it out if you're trying to find more information. So the last thing I want to say before we get into it is that if you have a question, if you have anything to say, if you want to curse at me for some reason, speak up. So what are we going to do here? Like the title said, we're going to work on developing a JavaScript SDK from our Haskell types. And what does that really mean? That means we're going to do some practical code generation. We're going to do some type reflection. We're going to kind of gloss over GADTs. We're going to be using them. Talk about constraint kinds, scope type variables, and existential quantification. So, why are we doing this? We're doing this because large applications are complex. And the larger they get, the more complex they become. At SchedgeMe, we have about 200 APIs and over 100 exposed data types. And our Haskell backend does a great job of allowing us to kind of wrangle this complexity. But our JavaScript front end constantly is having problems bubble up from the Haskell backend.
Can you put the mic
Closer?
closer?
Sure. I'm too quiet. How's that? Better? More projection? Okay, so our Haskell backend does a great job of allowing us to kind of wrangle this complexity, but the JavaScript front end doesn't really have many tools for that. So when we talk about the tools on our Haskell side, we have static types, type inference, immutability, descriptive error messages, myriads of warnings that help us with areas where we don't have exhaustiveness checks. And we can kind of toggle these things on and off depending on what level of safety and what kind of help we're looking for out of GHC or any other Haskell compiler we're using. Haskell loves you. Haskell wants you to be successful. It wants to help you take care of all of this complexity and just really be able to move quickly with it. JavaScript, on the other hand, the tools that it has for dealing with complexity, it's not much. It has a huge amount of incidental complexity, and it's really, really easy to build a very large application in JavaScript. But once you get beyond that building side of it, you get into the land of maintenance. And there are absolutely no tools in JavaScript to allow you to maintain them. And every single time you have to do something, you have to keep the entire application state in your head. You have to remember all of the control flow, every last little thing. And it's extremely taxing, and it's something that just leads to failure. There's no other path that you're going to go down other than breaking things and having bugs. So, how do you get around that? Well, you write tests. You write a lot of tests. You write a shit ton of tests. And with the rise of dynamic languages and their maturation, we've kind of seen the rise of TDD, test-driven development. And we've also seen the death of TDD as people have learned that it's actually kind of a bad idea in some ways, a good idea in other ways. It really results in having these massive test suites where you're just checking every last little thing. And it turns out that a lot of the things that you're checking are types. And you're just doing the job of what a compiler should be doing. And you're doing it badly because you're relying on humans to do the job. You're relying on them to be smart enough and to have a mechanistic perspective on things. So it slows the pace of innovation, and every single time you want to get something up to production or even up to a staging server, you have to run this huge suite that takes forever, and it sucks. So we're Haskell programmers. We love types. They're our friend. They're well specified. They allow us to have strong guarantees. And so, why not lean on that correctness? Why not use our Haskell types as a schema for every other situation that we have? Why not turn our Haskell types into a data provider? So after I've said all this stuff about JavaScript, why use JavaScript, you might ask? Why are we using JavaScript at SchedgeMe in the first place? There are all these alternatives, all these different things that have varying degrees of safety, things that are similar to Haskell. And there's even GHCJS, which is maturing extremely fastly, and you should probably consider using if you're starting a new project. But at SCHME, we're stuck with it. Before all these things were pretty immature, and we weren't really ready to make that jump, and the cost benefit wasn't really there. So we built a large front end in JavaScript, and now we have to maintain it. So why can't Haskell and JavaScript be friends? Why can't we make this communication better? Why can't we stop all of these problems from bubbling up from the server every single time we just want to change a data type or adjust something which is very minute but might have sweeping changes across the system? So we're here to talk about developing an SDK. So what is that? What is that to us? When we came to this project, we set our requirements. And we wanted our types to originate from Haskell. We wanted to have automatic encoding and decoding from JSON into these types that we're building in JavaScript. We wanted it to be, statically typed, or as close to statically typed as we could get with the current JavaScript typing technology. And, why not have immutability? We know this gives us a lot of guarantees. It reduces complexity greatly. So let's just throw it in there for the hell of it. So in no specific order, we're going to run through some of these requirements. For static types, we chose Closure Compiler. This is partially a decision based on history. We were already using it. And partially a decision based on where this piece of technology is. There are other players in this JavaScript type spectrum now. There's Flow, there's TypeScript, there's AtScript. Somebody in the Haskell community, I'm pretty sure, is working on a typed variant of JavaScript. But Closure Compiler is pretty mature. It's got a generally nice system. It has really great compilation strategies, and it can do a lot to help you in reducing the size of your code and also removing redundancy and increasing performance. And actually, if you use your types aggressively enough, it will lean on your types to do more. So, immutability. We're freezing things aggressively. JavaScript has object.freeze, which will not allow you to change any properties on an object. And we're also using David Nolan's Mori library, which is something that's come out of the Clojure community. It's maps, sets, vectors, and just immutable data structures. And we're kind of wrapping that in a bit of a facade so that we can have it be well-typed. Because it comes from Clojure, it's dynamic in nature. So we don't like that.
Question on JavaScript JIT optimization. Do you know if any current JS kits take advantage of frozenness of objects?
No.
Optimized?
No, they're not currently. They've only recently, probably within like the last 6 months, gotten beyond the point where frozen objects were actually a performance decrease. So the issue there was that if you had an object and it was just in some vanilla object state, they had a very small representation that they could do for that. If you were doing any other kinds of properties on an object, like setters and getters and frozen and on all these other kind of things that you can do to properties on an object, it was a much larger, less optimized state for that object. So freezing something would add a little bit of a decrease in performance, but that was only on objects that were really like 6 properties and under. But they fixed that. So eventually, we're hoping as immutability kind of becomes more of a thing in the JavaScript world, they'll start taking advantage of that, which they obviously can, if it can be safe enough. So, now the rest of the talk. We've covered 2 of our bullet points, and now we're actually going to delve into some code examples and how we're actually going to do this thing. So, in order to create an SDK, we have to think about how are we talking to our server? How do we know about our types? Well, our routes are our access point to data with a server, but they're also our access point to our types. If we know what all of our routes are, we can delve into those, we can see which types they expose, and delve even further into those types to see what types they know about. We can spider in this way. So our routes and our types are just, they are the key to this entire thing. So for routes, we're just using a GADT. Here's a simple example. It's adding some type safety over what the request and response. Yes?
So routes, how are you actually discovering content types, or you just like?
This is exactly what we're going to talk about. So we've got a request and a response. You know, there's a little bit of type safety here. But this isn't really saying much beyond a data structure. So we have a type class called sub-API, which allows us to construct URLs, methods, handlers, and grab some documentation, which we'll delve into further later. So here's a simple example of that. It's not extremely complex. It's not extremely pretty. But it's simple. It's straightforward. This is something that we like at SketchMe. We like to not get terribly fancy. We want something that's easily manageable and that the majority of people can wrap their head around quickly. So after we have our concept of what a route looks like, let's talk about types. So what is a type going to look like in JavaScript? How do we get from a Haskell type to a JavaScript type? Well, the first thing that we're going to need is we're going to need some sort of abstract, syntax tree of what a JavaScript object is. So we have this JS typable type class that has a function JS type. And you notice JS typable, we're setting this over top of some type. A is a type. Then we're going to need to actually be able to construct this and generate some stringly typed JavaScript body. So we have JS constructor. Then we're going to need to know about what the JSON representation is going to look like. So we have JSON type, which returns a JSON AST. And we have, we need a way to know which function we're actually going to call in JavaScript to turn this from a JSON representation into the actual object representation. In most cases, this is going to end up being an object or a function called like from JSON or something like that. And then we have a way to kind of reify the different types that this type knows about. So you can assume some JS typable, we're going to go into this more later, is a representation of a type. And we are returning a set of types from this. And finally, how about some documentation? We can return documentation too. So something that you might notice here is that the majority of these functions are acting upon proxies. And if you've never worked with a proxy before, you might be wondering, what is that? What's a proxy? What does this all mean? So data.proxy it's kind of a way of talking about a type without actually having a value of that type. It's simply just a nullary type with a phantom type on it. So I can say, I want to talk about ints, so I'll have a proxy of type proxy int. I want to talk about strings, so proxy of proxy string, and so on. We can get complex types. And in this way, we're able to dispatch on functions talking about a type without actually having to have the full instantiated value of that. Because in the case of a complex type, there might be 200 types below this that we'd have to construct. So we don't want to actually have that type in memory. We just want to talk about the type. So here's a simple derivation of our JS typable. This is a string. For its JS type, it's a JS string. For its JSON type, it's a JSON string. And when we go to decode it, we're just accessing the property because a JavaScript string and a JSON string are the same exact thing. A more complex example of this might be a list. You can see this is starting to get a little more out of hand. The actual instance of this type class is a little bit larger. But you can see a JS array is dispatching on whatever type is inside of it. Same with the JSON array. And we're leveraging our vector representation, which is just a wrapper around David Nolan's Maury. And get types, you can see it's wrapping that proxy inside of our some JS typable and returning a singleton set. So it's able to communicate and say, hey, I know about this other type. So that could get out of hand. So we use template Haskell for most of these things. These derivations are extremely mechanistic, and this is exactly what template Haskell is for. And we could, I could go into showing you all of this template Haskell, but it's template Haskell. It's mostly inscrutable, and we could spend the rest of the talk just looking at this stuff. And no one wants to look at template Haskell, unless you do, and I'll give a talk on it. So after we know what our types look like, how do we go about reifying them? How do we pull them out of our Haskell source? So these types right here are the key to this. And their footprint is very small. And they're actually kind of complex. If you look at it and you're not familiar with some of these concepts, you're staring at that saying, I have no idea what that's going to do. So let's take it one at a time. Let's just break these down into their core concepts, and we'll come back and talk about that. So first, we're using constraint kinds. Oh, you know what? I was actually supposed to fix this slide. This won't compile. But we'll talk about the concept. Constraint kinds allow us to speak about our type constraints as if they're on the right side of our type. So normally you would put a constraint if we were constraining something to a num type. We'd have num a and then fat arrow and then a, saying this is constrained as a num. With constraint kinds, we can say this type has a constraint, and then we're able to pass that constraint around like an argument to our type. So we can be a little more generic about our constraints instead of pinning functions specifically to different constraints. We're also using existentially quantified types. When you first encounter this, it seems pretty heady, but then the intuition starts to build pretty quickly. So what's going on here is, you can see on our data type up here, we have some real, which doesn't have any type parameters on the left hand, but it does have type parameters on the right hand. This is normally something that wouldn't compile in GHC. But using existentially quantified types, we can say we have an A here, and we know something about it. We know that A is a real. So anything that we use inside of some real must be able to have functions from the type class real dispatched upon it. So we're basically wrapping these things inside of a box and saying, I don't know anything about this except for that it's a real. And so those are the only functions that we can actually enact upon it. So we can have a double and a float inside of a list, and we get a heterogeneous list in that way. It's a very specific heterogeneous list. It's a heterogeneous list of reals, but we're able to unify types that are very disparate. A simple example of this is, say that we have some jacks and we have some bouncy balls, and we put each of those in a separate box and we close them up. And we put a label on them that say, I can play jacks with these. So we can say that this is a box of these two boxes contain the same things, because we know if we open them up, we can play jacks with them. But they're still very separate things. Is that making sense to everyone? Am I leaving anybody behind here? Okay, cool. Remember, speak up. So now that we have these, this might be a little bit clearer. It might not be, but it might be. So for some JS typable, we're using existentially quantified types. We are constraining it on a JS typable, and we're wrapping it inside of this constructor of some JS typable. So we know anything that is inside of a some JS typable, we can act on that with JS typable functions. Then we have this very small GADT here, which we're using constraint kinds on, in order to add some constraints to the B and the C of our type A, which is a star to star to star kind. And that's just a type that's mirroring the structure of our routes. So you can think of this as a type that's wrapping over our routes with a certain type of constraint. And then our enum2 type class just allows us to reify those sum2s with some context. In most cases here, we're going to be using the context of JS typable. Everybody got it? All right. So this is how we reify the API. We've got our all2.js API, and we're constraining that on sub API, as well as enum2 JS typable, and we're passing it a proxy of that API. And from this, we're able to call enum2 on that type, on that K from the proxy. And then we're able to map over it with 2.js API after we've unwrapped what was inside of our sum2. After we've gained access to this thing that the compiler doesn't really know anything about, it just knows that it can do JS typable stuff on. And so we call 2.js API on that, which is basically just a way to wrap these things inside of a common type. So we're taking all these disparate types, and we're building a kind of API method representation from them. So then we have a common thing to then generate some sort of JavaScript representation from. So something, again, you might notice, there's another concept hidden inside of here, is that we're using type variables from our top level inside of our function. This is something that would not usually compile. But we're using scope type variables. So the only way to really describe scoped type variables is to show you what GHC does when it sees a type variable. So when we do something like this, ID is A to A, and the implementation is X to X, X equals X. GHC sees this. It inserts a universal quantification for A, saying, I know that all A's are A's. And it hides that from us because it's mostly noise. We don't really need to do this in the vast majority of cases. But what if we had a really complex function and we just wanted to kind of clear some things up and just add a little bit of documentation inside of this dense thing saying, this right here, this variable is an A. Well, this won't compile. Because what GHC does is for every single type, it inserts a quantification. So we have for all A to A, and ID is X equals X, which is a for all A to A. And we get this error, which at first glance seems pretty ridiculous, and probably is, but after you've seen it a few times, you start to get used to reading these, and they start to make a little more sense. So you can grow a kind of perception of what this means. But really, we can break this all down pretty simple. This is what GHC sees. It sees a completely different type. That quantification says all of these A's are A's within this scope. So we have an A to A, and the X is a B. So this is bad. This won't unify. We can't compile this. So what we really need to do is use scope type variables, where we actually include our quantification. And what including this quantification does is it says GHC, all A's inside of this scope are A's. I don't want you to introduce any more quantifications for A's. Just believe me, they're all A's. So now this will compile. GHC believes us. It says, yes, that A is an A. So if we run back real quick. In this example here, we're using K up in this top function, all2.js API, as well as in the function below here, we're using our request and response that we're pulling out of our type constraints. So we're able to talk about these types just from their constraints, and we're able to turn them into proxies so we can dispatch on this type class. So we don't actually have to have implementations of these things in hand. We can just talk about them in a very, very roundabout way. So let's leverage scope type variables in order to reify all of our types. So this is a little more intensive, but our types are looking very similar. We have our quantification, which is signaling to GHC that all A's and all K's in this function are A's and K's. Don't give me any more quantifications. And we're saying it's a sub API. We're using enum2, constraining it to JS typable on that K. And we're passing it a proxy. Our proxies, again, are eyes out. And here, we're able to open up those sum2s after we've run enum2 and ask for the request and the response proxy, because now our sum2 is a representation of that API. And so in request and response, we're leveraging that request and response constraint using I can't say that for some reason, scope type variables in order to generate proxies from request and response and spider over those types, unioning them together. And in spider types, we are calling a function called Transitive Closure. So this is going to need some description. This concept of a transitive closure is that if you think about your types, and you thought about asking each type what it knows about, and then going to that type and asking it what it knows about, and then going in that chain, chances are your types are going to create a loop. You're going to get some infinite recursion in that situation if one type knows about a type that knows about that type that you were originally talking about, which is very common. Even if you have a recursive type, this will happen. And recursive types are a bread and butter element. So our transitive closure, we're talking about give me all of the sum of the knowledge, but stop when you've learned as much as you can. So here's our implementation of the transitive closure. It's using sets, and it's taking a function that, in this case, the function that we're using is getTypes. This is our function from JS typable, which is asking that type, what other types do you know about? And it takes a set of the things that we do know about. So this might be just a singleton set of some type that we're running across. In the case back here, it's the request or the response type. And so we run through here, and we run this function go. And we say, hand go all of the things that I already know about, and hand it the things that I've just learned about. And so if the things that you've just learned about are nothing, you can't learn any more, return the things that I know. I've done learning. I have everything that I need to know. Otherwise, we want to run through, we want to run through this list of things that we've just learned about, and we want to pull all of their, we want to call that getTypes. We say, I've just learned about these things, they might know more things. So we get all of the types from those, and then we get a difference of our existing types and those sub-dependencies to see if there's anything new that's come out of this. And then we pass the union of our existing and our sub-dependencies along with the new things that we know. And eventually, this is going to result in a null set because we've reached all of the points of our graph of types. So at this point, we're done. We've been able to reify our API. We've been able to reify all of our types. And from that, we can run over these proxies and call all of our JS typable functions on it. We can get our AST for our JSON. We can get our AST for our JavaScript. We can build JavaScript bodies. We can call our decoding function, and we can get documentation. And that's the one thing that we haven't really covered yet, documentation. So our requirements for documentation were that we wanted it to be user-focused. We don't want this to be for our developers. This is documentation for people consuming our API. And we want it to be type-safe because. Do I need to explain why it should be type-safe? I don't know. This seems like a crowd that appreciates that. So what about Haddock? We've got this thing, Haddock. It's meant for generating documentation. Does a great job of it. But Haddock is for people working on the Haskell. Haddock is internal documentation. It's not external documentation. And do we really want to find some kind of gross way of combining our external documentation inside of our Haddocks and pulling that out? It starts to muddy the waters. We want external, internal. We want to keep them in separate worlds. So, that ruled Haddock out. Oh, also to add in the fact that Haddock is not type safe. It's built upon proximity, and there's a bit of hairiness in proximity parsing for documentation. So there is this one feature in GHC which is little used. I think it's really only used by the compiler team because they built it for themselves. Annotations. So in Haskell, we have this thing called an annotation, which we can attach to a type. So here's the way it's done. You have an, we wrap it in this kind of pragma-y looking comment. You have an on for annotation. It's on a type. The type that it's on is foo, and we attach some arbitrary data. In this case, we're attaching a string. And we get that out through template Haskell by arrayifying that annotation and getting back a Q string inside of a quasi-monad. Only time I've said monad, I'm sorry. And we can also attach this to just arbitrary functions, including default functions inside of a type itself. So it's separate from Haddock. It doesn't muddy the waters of what is user, what is internal. It's type safe, because if we remove Baz, we're going to get a compile error because the annotation now has no idea how to attach itself to something in the source. And we can give it any kind of data. So we have got this doc data type that we can attach to it, and we can have all of this great metadata about these things that users might want to know. And one thing to note, it would be really great if we could remove that deprecated flag, because GHC has a way of deprecating things, but we have no way of rayifying that via template Haskell or some other method. So if anybody from the compiler team ever watches this, I want to get this out. I don't want to have the doc deprecated inside of this. So let's do a little demo. Let's look at what this actually looks like. Now I actually have to get this mouse to not suck. So I should have pulled this up first. So first we're going to look at what our documentation looks like. Oh, and I don't have internet. What was the Wi-Fi? Pivotal guest and.
Make it happen.
Yes, it is. What in the hell? Is there an Ethernet connection up here? Sorry, guys. This is something I should have done first. Fiddle guest. Let's make it happen. Cool. Okay. And now let's see if we can get on it. Connecting. Ah, there we are. Okay, so documentation. This is something that no one wants to write, and only a few people want to read. So, I'm going to have to look this way. So this is what our documentation looks like. Here, oh, we're a little cut off too. So we've got APIs, we've got types, and we can kind of spider through these. Here we have an attendee field find and read, and okay, what is an attendee field? Let's jump through that, and so on and so on. And we can pull out all this information, giving us, if these were a little bit more documented, there would be more content, but we're still working all of that. But we have all of the fields that are on this type, including their types, which are written in this kind of pseudo-Java-esque generic thing that Closure compiler and many other languages use. So we want to be friendly. We want to use some type kind of syntax that is available to most developers. And we've got our JSON representation down here, which is written in a kind of JSON doc-esque. We have got booked at string and so forth. And so we're able to get some pretty comprehensive documentation.
Can you zoom in?
Can I zoom in? Yeah. Sure. Who knows what that'll do to the styles? Oh, God. Is that zoomed in enough? I wish I could mirror this back. So yeah, so this is, we're able to build this huge, huge list of documentation. Where'd my mouse go? There it is. We've got all these types. Look at all these types. This would be horrible to maintain ourselves. So we're able to generate it. And as far as JavaScript, let's pull something up here. Oops. I don't have it built. All right, I'm not going to build this stuff in front of you. Let's actually go into... Here, I'm going to pull this back for a second, and I'm going to grab some of it and throw it in there. Actually, it'd probably be a pretty good idea just to serve that stuff from this documentation. I'll have to make a note of that. Let's see. Oh, one sec. If I were smart, I would have queued this up. So we have here we have some output. You can see all of these Closure compiler JS doc types that are being added to all this. And make it larger, yeah. How big will it get? Let me pull this up more. Is that good? Should be bigger. A little bigger? Say when. All right, let's get a little ridiculous. So we've got this API that's being generated, which has all of our types, our request type, our return type, which is being wrapped inside of a future just to manage that asynchronous nature of it. And these things are extremely regular because we're generating them, and we don't have to worry about, how are we going to implement this one feature, and these things kind of just suddenly diverging in their form. So we have all of those, tons and tons of APIs, which are doing our decoding and encoding for us. And then we have tons and tons and tons of types. So let's find one that is a larger type, like a record type of some sort. So here you go. Here is a record type, an add-on rule set, which has a property of max add-ons and max time, min add-ons, and all of this is coming directly from our Haskell. We don't have to touch any of this. This is all just generated code that will work out of the box, and it's extremely annotated because we're really trying to get Closure compiler to do its job. So yeah, so this is the quick demo of this stuff. And so if you guys will indulge me for one moment, I'd like to make a very stilted analogy. Oh, that didn't go. Let's go over here. I'd like you guys to consider this chair. This is my stilted analogy. So, this chair is very simple. elegant in a way. It's sturdy. And it was built by people that thought very, very deeply about their craft and tried to find the very best way in order to do something. Can anybody guess who those people were? No. I thought I heard it. It was built by the Shakers. And if anybody knows anything about the Shakers, you know that they're all dead. The Shakers were a group of people which were very contemplative and spent a lot of time on their craft and wanted to do the very, very best job at it. But they were also very insular. And they didn't broaden their community. And they didn't interact nicely with everyone else. And they were also celibate. So, all of their great ideas that they spent so much time thinking about and developing, well, they died with them. And now no one really knows how this chair was constructed. We can guess it, we can take it apart. But the thing here is that the Haskell community is doing amazing things. And there are plenty of people that are doing a great, great job reaching out to other communities and building bridges. But there's still a big, strong strain in the Haskell community that says if it's not Haskell, it's not good. And we need to break that. We need to build bridges, because the only way to bring more people in and to get more people doing Haskell jobs is to get them interested through compassion and through good ideas and through talking to them with the language that they know. So those people who are doing these great things, keep doing them better. And those people who are looking to get into Haskell, and maybe you're a Objective-C expert, maybe you're a Ruby expert or something like that. A great project to start with is building a bridge. Get your people from your community interested in Haskell by making it easy, getting them in through an easy path. So, after I've preached at you, any questions?
Big one. Is this library open source? And if so, where can I get it?
It's not open source. We would love to open source it, but there's certain elements of it that right now would not be friendly to that. There's a few reasons. One, we have some kind of proprietary, or not really proprietary, but some custom JSON representations that we've tacked on to ASIN. And we've got just a few other things that are very SketchMe specific. But we'd love to be able to kind of claw those out and have them be a separate part and have the core library that we can open source. Anybody else? So this is something that we're still...
Can you repeat her question, please?
Yeah, so she was wondering that I mentioned how in order to build a JavaScript application, you need tests. And has our methodology changed now that we're introducing this new kind of more type-safe generated version of JavaScript? And for right now, it hasn't changed much because we're currently in the process of implementing it. But a nice thing is that we're seeing more type errors. So we're moving in the right direction. When we see errors based on types, that's good. Anybody else?
So what's the real world experience like? Like when you have a bug in production, do you have a line number? Do you use source maps for that? You know, how does that all work?
So this is just literate JavaScript. There's nothing about this. This is not Flow. This is not TypeScript. This is not some kind of dialect that you then have to compile down to some other representation. This is just JavaScript, and that was a big part of it. We didn't want to have some other kind of mechanism in the way of getting access to this and people using it. Because this is intended, not only are we going to use it, we're going to eat our own dog food, but this is intended for other people to use with our system.
This is clearly a really big task, and you kind of dismissed GHCJS, haste, etc. up front, but you didn't really say why. And wouldn't it have been just as big of a job to rewrite it in GHCJS? So why did you particularly need to do this as opposed to before?
So there's been a lot of people who have talked about this subject of I have something, but I could do it better, so let's tear it all down and build it again. And it's really, really hard to duplicate your current functionality when you've started completely from the beginning, because there's a lot of social artifacts and just different little tiny quirks in an implementation that come out of that process of sending something into production and having clients comment upon it and say, oh no, this thing should be blue right here, or when I touch that it should go the other way, and it's really hard to catch all of that. Well, no, we're just generating types. We're generating types and APIs. We're not actually generating the logic and the business logic and the presentation logic.
You're generating an API that other JavaScript programmers can call.
Yes, and the types that they will interact with once they've called that API. Yeah. Anybody else?
I have a general beginner's question.
Mm-hmm.
With respect to building bridges, etc. Can you comment on the strengths and suitability of Haskell for data analysis tasks?
For data analysis tasks, I can't specifically comment upon that, but there is a great talk that happened at the Compose conference that I'm not sure, Doug, do you know if it's up? It was the robots on Haskell? Yeah, so he actually talks specifically about consuming data that might be changing and in this kind of data analysis realm. So I would check out that talk. It's robots on Haskell or Haskell on robots. Well, something is mounting something. Anybody else? All right.
All right.
Thank you, guys.
Thanks, Evan.